Well, good afternoon. This is our lecture for beginning of lecture material for Module 7, which is organic chemistry. We're going to be talking about, an introduction to organic chemistry. We're going to be talking about hydrocarbons of various types, and then we're going to be talking about a few other functionalized organic compounds such as alcohols, thiols. I think we're going to mention ethers, carboxylic acids, aldehydes, ketones, and maybe one or two others. This is going to be very different from what you've seen previous to this lecture. This is organic compounds. Organic chemistry is a rather distinctive field. It is defined in large part by a peculiarity of carbon. Carbon can form long chains of carbon atoms bonded to each other with single covalent bonds and sometimes double or triple covalent bonds. And that's something that other elements really cannot do to the extent that carbon can. Essentially, carbon can form molecules of long chains of indefinite length. We don't know of any limit to that. That is not true of other elements. Nitrogen, I think, can form maybe three or at most four nitrogen chains. Silicon really, I think, analogs of like ethane, we'll see what ethane is, of silicon really are very unstable. Sulfur can form slightly longer chains, but for the most part, elements don't like to bond to each other, or at least nonmetals. You have the halogens, they'll form diatomic molecules. Oxygen will form diatomic molecules. But carbon has this peculiarity where it can actually make long chains of carbon atoms. And the ability to form 4 covalent bonds, each carbon, allows an enormous number of compounds to be formed. And of course, biological molecules are mostly organic molecules. In fact, the term organic comes from an earlier belief that organic compounds could only be made by living organisms. Well, we found out later on that that isn't true, but let's get into this and you'll see what it's like. We have this. This is going to be in your textbook. There's going to be more detail on this in your text if you want to read about it. Organic chemistry, as I've already hinted, is the study of carbon compounds. Now, you're familiar with a lot of carbon compounds. I'm talking about organic compounds. Vegetable oil contains carbon and hydrogen, which is the fundamental, the most basic type of organic compound is a compound of carbon and hydrogen, hydrocarbons. Now, vegetable oil also contains some oxygen in it. We're going to see when we talk about fats the structures of those things. Just about everything biological contains carbon and hydrogen, and they're therefore organic molecules. Petroleum, natural gas, coal, those are organic materials as well. And what we're going to do today is, to begin with this section, we're going to identify properties characteristic of organic compared with inorganic compounds. So let's take a look at these. An organic compound, at its most basic, is a compound of carbon and hydrogen. There's a few other elements that show up as well, and we're going to be seeing plenty of those as we go along. There's some nonmetals, mostly nonmetals. In fact, you really don't see, there is such a thing as an organometallic compound, but they tend not to be very stable, and they're really not that relevant to biochemistry. Although there's a few, you'll find a few compounds, you'll find a few proteins that contain metal ions like hemoglobin. But for the most part, it's oxygen, sulfur, nitrogen, phosphorus, and or a halogen. Halogen doesn't show up in too many compounds in biochemical systems, but it does show up in a few. And you find organic compounds in a lot of common products: gasoline, medicines, shampoos, plastics, and perfumes. In fact, plastics are what they are because of the fact that carbon can form long chains of carbon atoms. You take polyethylene, polypropylene, those are really long carbon, just gigantic hydrocarbons. The way we write the formulas is pretty much the same as the others, with the symbol with a subscript indicating the number of atoms per molecule. We write these in first with carbon first, followed by hydrogen, and then any other element. So you're going to see C something, H C sub something, H sub something, and then O, N, S, various other things. Organic compounds, you might remember this when we were talking about ionic bonding and covalent bonding, covalent bonding, molecular compounds. Organic compounds are covalently bonded. That means their electron pairs are shared between bonding atoms. The intermolecular forces tend to be fairly low because at least the hydrocarbons are very nonpolar. They have low melting and boiling points. A good example is methane, and I don't know offhand what the boiling point of methane is. If I can see it here, I don't know if I find one. I don't see it in the text here. They do have the boiling point of propane, for example, which is something like it was minus 42 degrees Celsius here, and it's pretty low. And you compare that to water, which has a much lower molecular weight, and its boiling point is 100 degrees Celsius. And then you have, and that's an inorganic compound, but then you have the more traditional, the more distinctive inorganic compounds, which is a metal and a non-metal. You have things like sodium chloride, for example, which is going to boil at over 1400 degrees Celsius, which is very high. So the bonding is a lot different. Typical inorganic compounds, and I used water as an example. There are some molecular compounds, but the typical inorganic compound that you think of is going to be a metal and a non-metal, or a polyatomic anion with it, and they tend to melt very high and boil very high. Organic compounds tend to be flammable. They will undergo combustion, and they're not soluble in water. Oil and water don't mix. That's vegetable oil is a mixture of organic compounds. It's not soluble in water. It's not really a hydrocarbon, but it is mostly carbon and hydrogen. There is really not a lot of anything else in there. There's some oxygen in it, but we'll see how they're set up when we get into the biochemistry. As I said here, inorganic compounds have high melting points and boiling points, and they're usually, or at least often, soluble in water. Most of them do not burn in air. So you take the contrast between propane, which is an organic compound which is used as a fuel. Salt, sodium chloride, is an inorganic compound composed of sodium and chloride ions. So you see the propane is a molecular compound, and sodium chloride is an ionic compound. So that's a really fundamental difference between inorganic and organic compounds. And here's this is table 11.1 in your text. I highlighted two of the cells in the table because these are very important in understanding organic compounds. Starting at the most basic, at the hydrocarbon level, they're nonpolar unless there's a strongly electronegative atom present, and they're not soluble in water unless there's a polar group present. So you do have some organic compounds that are like ethyl alcohol. That's soluble in water. Isopropyl alcohol, rubbing alcohol, that's soluble in water. You buy isopropyl alcohol as I think it's a 70% solution. I think that's the percentage. So there are some organic compounds that dissolve in water, but we're going to see some of the trends as we go along. We're going to see some of the trends in solubility and how it works. So you study this table. This is in your textbook. You're going to see that these are really different organic compounds really are distinctive compared with inorganic compounds. You're going to see this is going to be a lot different from what you've seen in the past. We're not going to be doing a lot of the chemistry, though. We're going to be just talking about the structures and naming them for the most part. But you're going to need to know this to do the biochemistry part of the course. So let's look at a learning check here. You look at these properties and you pick, well, is it typical of a compound that's inorganic or organic? So let's look at this, a high melting point. Well, high melting point is going to be large. Remember, high melting point, that means the interparticle or interatomic, intermolecular forces are going to be very high. So that's going to be typical of an ionic bond. I've said this a number of times. The electrostatic attraction, the electrical attraction for positive and negative ions is very strong. It's very hard to separate charges in general. So that's going to be inorganic. B is not soluble in water. Well, not soluble in water means it's not polar. Now, there are inorganic compounds that are not soluble in water, but you know from experience, you know from earlier parts of this course that a lot of inorganic compounds are soluble in water, particularly ionic compounds. So not soluble in water is going to be organic. And having the formula now, there's C3, CH2, CH3. Well, we talked about, I mentioned the typical or the quintessential basic organic molecule is a hydrocarbon, an alkane, which is what you have there is propane, so that's organic. Formula MgCl2, well, it's magnesium chloride. That's inorganic. If you don't have any carbon or hydrogen, it's not an organic molecule. You might see some books, it's like or carbon tetrachloride, for example. Conceivably, you could call some compounds without hydrogen organic to some extent, but it's basically carbon and hydrogen in there. If carbon and hydrogen are in there and you've got covalent bonds, it's organic. So magnesium chloride is an inorganic compound. Burning easily in air, that's typical of hydrocarbons. That's typical of organic compounds. That's wood fires, coal, natural gas, and all our fuels. All our main fuels are organic right now. People are working on developing hydrogen, but that's it. It is commercial at a limited level, but for the most part, our fuels are still, our energy sources are still organic compounds. So they burn easily in air. Covalent bonds, that's going to be typical of organic. Now, there is overlap here, all right? But these are generalizations. There's exceptions. You aren't going to run into the exceptions very often. So these generalizations you've been given are going to hold for most of what you experience in your careers and anything that has to do with biochemistry. So you see the high melting point, that inorganic, and then two organic compounds, magnesium chloride's inorganic, and organic compounds burn easily in air and have covalent compounds. Okay, I missed that capitalization there. Okay, now we get into hydrocarbons. So now we're getting into organic chemistry per se. Simple definition: hydrocarbons are organic compounds that contain only carbon and hydrogen. In organic molecules, every carbon has 4 bonds. You might find the 4 bonds distributed a little differently. A carbon atom like what you see there, that's a methane molecule, CH4. It's a saturated hydrocarbon and it contains only single bonds. But there are other carbon compounds that contain double and triple bonds as well. So there's still 4 bonds. Every stable carbon compound has 4 bonds. Every carbon atom in a stable organic compound has 4 bonds to it. So saturated hydrocarbons, which we also call alkanes, which we'll see that term shortly, they contain only single bonds. So the one you have here, I think you can see my cursor. The the one I'm looking at right now is methane CH4, and then you have a 2-carbon chain, which the rest of the bonds are to hydrogen. That's ethane. Those are saturated hydrocarbons. And you're going to use methane as an example for describing some of the different ways of representing organic compounds. There's a number of different methods of representing these, of drawing these compounds. And here they are. There's 5 of them. You have a, what we call a space-filling model, a ball and stick model, a wedge dash model, expanded structural formula, and condensed structural formula. Now, let's just briefly describe these things. A space-filling model is intended to represent something like what we feel the molecule actually looks like, or how it's structured, how it would look if you could actually magnify it or shrink down to a small enough size where you could actually see a molecule. It would look something like that. Ball and stick models are really useful for demonstrating what we call stereochemistry. Stereochemistry is the study of 3-dimensional properties of molecules. And that when you see there's still the central carbon and 4 hydrogen atoms, which are, the central carbon is represented as a black ball. White balls are a little smaller, and they represent hydrogen. And then you have sticks that plug into the holes in the oxygen, or the carbon atom. The carbon atom, I'm putting carbon in the carbon atom in parentheses because it's actually this is a model. And in fact, I have molecular models which are set up like that. We're not going to really need them here, though. Now, the wedge dash model is a way of representing 3-dimensional structures in 2 dimensions. And I think you probably can guess already that the wedges, the solid wedges, you think about it, kind of looks like that one solid wedge in number C, the one in the middle there. That black wedge, it kind of looks like the hydrogen is coming out of the paper at you, and the dashed wedge that's intended to show that it's actually going in behind the plane of the paper, and the solid lines, the straight line, the simple solid lines represent the hydrogen atoms, and those are in the plane of the paper. So it's a way of representing a 3-dimensional structure where you need to know the 3-dimensional structure. And then the expanded structural formula is simply the carbon with 4 bonds. They put these things at right angles. And as you see, from the 3-dimensional structures, particularly B, they give you the 109-degree bond angle between the carbon-hydrogen bonds in the methane molecule. And then the condensed structural formula is really the way we're used to writing formulas. Now, you're going to see versions of condensed structural formulas that vary a little bit, but we'll see them as we go along. A lot of times, because of the number of organic compounds, a single formula can give rise to a lot of different compounds in a lot of cases. So sometimes you see the condensed structural formulas, less condensed or more condensed, depending on what the needs of the particular topic happen to be. So we have these 3 structures these 3 types of structures in ethane, and you see the space-filling model, ball and stick, wedge dash, expanded structural formula, condensed structural formula. So you can do this in principle with all organic molecules. And sometimes, in fact, sometimes you might actually have if you're focusing on just one carbon atom in a long carbon chain, you might just draw that one carbon in 3 dimensions and have the whole, have the rest of the molecule just represented by the capital letter R is very common for that as an alkyl group. But in general, these are the types of structural formulas that you're going to see. So let's take a look at the butane molecule and predict the shape around each carbon atom. Remember, with a saturated hydrocarbon, carbon has 4 bonds. Remember when we went back a few chapters ago, we talked about bond geometry, molecular geometry, the molecular shape, where if you have 4 electron groups, well, 4 bonding groups here especially, it's going to be tetrahedral. So the shape around each carbon atom is going to be tetrahedral. But let's see how they reason this out. They just say each carbon atom has 4 single covalent bonds and therefore a tetrahedral shape. And we've got it. Okay, so that's all there is for section 11.1. And I had been going one section at a time, but it seems we're moving along pretty well here. So I'm going to go ahead and go to section 2, 11.2, and we're going to continue with the description of alkanes. We're going to talk about alkanes in particular. So let me switch the presentation, and we'll get on with it. Okay, section 11.2 on alkanes. We're really going to just continue what we've started talking about. We're just going to get into more detail. A large number of carbon compounds is possible because of the covalent bonding between carbon atoms, because carbon can form a lot of bonds to itself. Notice there's a chain of 6 carbons there. You're not going to see a chain of 6 nitrogen atoms. You're not going to see a chain of 6 phosphorus atoms. Phosphorus will form molecules with 4 phosphorus atoms, but it really isn't a chain of phosphorus atoms. Silicon, there's some very unstable silicon compounds with 2 silicons bonded to each other. Silicon analogs of organic compounds, that is. So this is very unique, and you get these longer and longer chains. You are going to find that, well, this is C6H14. You're going to find that when you get into these things, you get into huge numbers of possible combinations of bonding combinations for that formula, C6H14. And it does mention there carbon-hydrogen bonds and carbon-carbon bonds are very strong. That's the point of carbon-carbon bonds. Carbon-carbon bonds are much stronger than bonds between atoms of other elements. There's fluorine in F2, very weak. Same as the others, chlorine, bromine, iodine. The bonds are relatively weak. They're easy to break. Oxygen and nitrogen are fairly strong bonds, and O2 and N2, but those are pretty much exceptions. And you don't really get longer chains. You get ozone with oxygen that's O3, but that's a very reactive molecule. It's really not that stable. So what we're trying to do here is, all we're really going to be trying to do in this section, though, is just write the IUPAC names, which are that's International Union of Pure and Applied Chemistry, and draw condensed structural and line angle formulas for alkanes and cycloalkanes. Okay, alkanes are hydrocarbons that contain only carbon-carbon and carbon-hydrogen single bonds. They form by a continuous chain of carbon atoms, and they're named using the IUPAC, International Union of Pure and Applied Chemistry system. Their names all end in ANE, ANE. And you're going to find that the naming of these things is very systematic, although there are a lot of rules you're going to have to learn in order to name these compounds, but it is manageable. The names of the compounds use Greek prefixes to name carbon chains with 5 or more carbon atoms, and we'll take a look at what they mean here. And this is something I sent this table around because it came to my attention last year that this particular table was not correct in some printings of this textbook. So I fixed this one up and I sent this along to you, and of course I'm going to post the slides, and I'm going to post of course the videos as well. But these are the different kinds of the different molecular formula, condensed structural formula, and line angle formula. We're going to talk about the line angle formula a little bit, but just show you the first 10 alkanes, the first 10 continuous chain unbranched alkanes, and that's what they're going to look like in the condensed structural formula and what we call a line angle formula. The condensed structural formula, you've already gotten an idea what that looks like. Each carbon and its attached hydrogen atoms are written as a group. Each single carbon atom and its attached hydrogen atoms are written as a group. The subscript indicates the number of hydrogen atoms bonded to that carbon atom. So what you see here is butane. You have CH3. That's 3 hydrogens attached to carbon. There is now 1 valence left over. There's room for 1 more bond, so that other bond goes to another carbon, which has 2 hydrogens attached, which is CH2. And that leaves another bond for another CH2 and then another CH3. So there's your structural formula for butane. So condensed structural formula is a little more on that. Alkanes can be written with structural formulas that are expanded to show each bond if you want to see each bond, and there can be reasons for that. And they can be condensed to show each carbon atom and its attached hydrogen atoms. And actually, when we get into substitutions, there's ways of writing the substituents as well. Now, these line angle formulas, they're also called skeletal formulas, are a shorthand, and they make use of the fact that organic compounds usually have a lot of carbon-hydrogen bonds and a lot of carbon-carbon bonds, and if you wrote them all down, some of these molecules could take a long time to write. So what you do is you use a line angles, a straight line by itself, which we don't see here, but you write a straight line is going to be 2. Actually, let's take a look at, go back a little bit here. You see this ethane, it's a straight line. Okay, that if you see that, that's an ethane molecule. And you write this you write long chains in a zigzag fashion, and the end of a chain and an angle represents a carbon atom. And if there's nothing written there, it represents, you assume that you assume hydrogen for all of the other bonds, other than the carbon-carbon bonds. So we'll see. So now let's go back to the table. You see propane. You see here there's 2 lines at an angle, and at the ends you would have a CH3, and in the middle that angle is a carbon, and the carbon's going to be attached to 2 other carbons. That's going to leave 2 bonds for something else, and if nothing else is written there, that something else is going to be hydrogen, or those something else's. So these are all, you see the representations of these compounds in the table in different type of structural formula notation. And notice methane, you don't have a line angle formula because it's just CH4, so you really don't have a line angle. You don't have a line angle formula for methane. It would be just a dot, which would probably lead to a lot of confusion and a lot of ambiguity, because you get punctuations and a dot also represents an odd electron. So you remember electron dot structures, for example. So we move on here. So you've got the 5 different ways of representing alkanes. And we don't, they don't say anything about the molecular formula. Well, molecular formula, ball and stick, expanded structural kinetics. They don't say anything about the space filling model, but there's that as well. Now we get into the structures. Depending on the needs of why you need to write the structure in the first place, some of that's going to determine what the method you use. So you can use an expanded structural formula if you want to draw the whole thing out for whatever reason, a condensed structural formula, or the line angle formulas. And okay, this is all butane. All of these are butane. And notice in the condensed structural formulas, something important to point out is that you don't have to draw these chains in straight lines. You can draw them zigzag. You can draw them at angles. You can notice we have the straight line here, and then these things are angled. All of these are angled. Well, here's a straight line. And here's a zigzag one. It looks almost like a line angle formula. And of course, a line angle formula, if you don't write the CH3s and CH2s, you got a line angle formula. So here, we'd give the following expanded structural formula: provide the molecular formula, the condensed structural formula, and the compound name. Well, we have a solution coming up, but let's go to the whiteboard and take a look at it. Now, if you look, you have a carbon, a carbon, a carbon, a carbon, and a carbon. I'm getting a little better at drawing these things. And anyway, these things are all filled in with hydrogens. I'm sucking on a cough drop to keep from coughing. I have issues with that, so when I talk a lot, so I need to do things about it. It's nothing serious. It's something that I have to deal with. Okay, well, there's the compound we have, and let's go back to where we were. Okay, we want the molecular formula, condensed structural formula, and the compound name. Okay, so let's do that. Molecular formula. Well, the molecular formula is going to be CXHY, where X and Y are going to be integers. So, well, we got 1, 2, 3, 4, 5 carbons. And we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So that's a molecular formula there. And we're done with that. Okay, A, molecular formula. B, what else are we looking for? Condensed structural formula. Okay? Well, condensed structural formula, you have just each carbon, and it's what's on it. And then you string the carbons together. 3, 4, 5. And I think it was the name of the compound they wanted, right? Yeah, the compound name. Okay, well, remember what we said. It's something ending in ane, E-N-E. So we know this is going to be something ane. This is a hydrocarbon, all carbon, and carbon hydrogen single bonds, saturated. It's an alkane, so it's something ending in ane. And except for the first 3, which are methane, ethane, and propane, everything else is a Greek prefix. And you have that table there, the table 11.2, and you can see the prefixes that are used. Well, on C5, the Greek prefix is going to be pent. and the name of the group is just pentane. All right. Now, let's see if we agree with the slides. And you see, we do. With C5H12, which is the molecular formula, and a condensed structural formula, the way we wrote it, and the compound name is pentane. So now they're asking for the condensed structural formula for ethane and heptane. Well, we can do that too. All right, let's do ethane and heptane. Condensed structural formula. Okay, we can zap this. Clear the canvas. What is it? Ethane and heptane. Okay. Ethane and heptane. Okay, well, ethane really doesn't give you any, the name ethane doesn't really give you any hint, but we know methane is 1 carbon, ethane is 2, propane is 3, so we know that. You really need to know that. So this is going to be 2 carbons, and let's see, what kind of formulas do we want? Condensed structural formula. Okay, so we want the condensed structural formula. All right, so you've got 2 carbons, so you're going to have 2 here, you're going to have a carbon here and a carbon here, and they're bonded together. So, and all the other bonds formed by carbon are going to be to hydrogen. So you're going to have a CH3. Remember, because you've got one of these tied up by one of the bonds tied up to carbon, and this carbon is one of its bonds tied up to the other carbon, and so you've got 3 bonds left. So it's going to be CH3. So that's going to be your condensed structural formula. Heptane is going to be a little more involved because its hept is 7. So, but we're going to have CH3 at the end. If you have a straight chain alkane, the 2 carbons on the end are going to be CH3, are going to have CH3 methyl groups, are going to be CH3, and everything in between is going to be CH2. So CH3, CH2, 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 4 there. This is 5. This is 6 carbons. And it's 7. So there's your condensed structural formulas. And when they do it, they get, it's a little neater because it's typeset, but all the same, those are your, you do have 7. That's the condensed structural formulas. You're done with that. Now, these things are going to continually get more complicated. You're going to find these molecules, alkanes can be a lot of different kinds of alkanes. And there's something called cycloalkanes. Cycloalkanes, well, cyclo, what does cyclo mean to you? Cycle. There's Greek word for circle. Is derived. The cyclo comes from the Greek word for circle. And there's no reason why, if these chains are long enough, that the end carbons cannot attach to each other, which is what happens in cyclopropane here. And you notice, okay, they're going to have 2 fewer hydrogens because of because each of the carbons, you look at propane, each of the end carbons are going to have to lose one of the hydrogens in order to be free to form a bond to the carbon on the other end. So you can see these things. These ring molecules are very common in chemistry. You're going to see a lot of these. A lot of amino acids have cyclic elements to their structures. There's DNA, nucleic acids are made of, well, sugars will form cyclic structures, and bases, what we call nitrogen, there's nitrogenous bases that are used to form DNA and RNA. They're cyclic molecules. So cyclic compounds are actually very common in chemistry. And to name these things, really all you do is take the parent hydrocarbon, how many the parent chain, how many carbons does it have? This one has 3, so you make a ring out of a 3-carbon alkane. You go from propane to cyclopropane. That's it. And these are the most common ring structures you'll see. In fact, 5 and 6 carbon rings are especially stable. 4 carbon rings aren't really that stable, but you see them once in a while. And then I'm not aware of too many cyclopropane rings in biochemistry, but you see them around a lot. In fact, cyclopropane is or was used as an anesthetic. I think it still might be a general anesthetic. So the way you represent them is pretty much the same way. You can use a ball and stick model, and there's space filling models can be done too. Condensed structural formulas, same way, and line angle formulas. Although line angle formulas, of course, you can have closed polygons. So, give the IUPAC name for each of the following compounds. All right. So, what you do is count the lines. You can count the lines, and here's what I'm gonna, let's see, that's 2, 4, 6, 8. It looks like 8. I'm gonna go to the whiteboard. It looks like there's 8 carbons on that one. Leave this here. Okay, 2, 4, 6, 8. Okay, there's that, 4 of these lines. You can draw these. I usually don't draw it this way. I just go bang, 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 bang like that. But you can do it this way. And you have an end. There's 1 there, 2, 3, 4, 5, 6, 7, 8. So this is going to be octane. We'll take a look at what the other one is. Okay, that's a pentagon. You recognize that as a pentagon. So 5 carbons. So it's going to be all angles here. All right. There's a carbon there. There's a carbon there. There's a carbon there. Carbon there. Carbon there. And these carbons are all going to have 2 hydrogens attached. And this is going to be it's going to be 5 carbon alkane, which is going to be a pentane, but it's a ring, so it's a cyclopentane. Let's see if I read the instructions right. Give the IUPAC name. Okay. So octane and cyclopentane, exactly as it said. Now we have name the following alkanes. And I don't think we have to write all this stuff out at this point, but they're all alkanes. You should be able to see that they're all alkanes. There's no anything else than carbon and hydrogen would be indicated somehow, or groups attached to the ring would be indicated somehow. So these are just straight alkanes. First one's 4 carbons. 4 carbons uses BUT, bute something. And it's an alkane, so it's butane. Cyclopropane, we've already seen cyclopropane. And then this one that looks like there's 8, 1, 2, 3, 4, 5, 6, it looks there's 8 there. So that's octane, 8, oct, from the Greek word for 8. And then this one's a ring, D is a ring, and it's a 6-membered ring, which means a 6-membered ring means there's 6 carbons in there. And it's an alkane, it's a cycloalkane. 6 is hex, so it's a hexane, and it's a ring, so it's cyclohexane. You see, that's how it looks. So we're done with 11.1 and 11.2, and we're going to continue with section 11.3. where we're talking about alkanes with substituents. Now, a little thought might indicate that, well, okay, you have there's a butane molecule there, and there's four bonds to each carbon, and there's no reason why. Okay, let's take the second carbon from the right and that butane molecule. Okay, so it's going to be, I guess this one here. Hopefully you can see the cursor. There's no reason that you can't replace one of those hydrogen atoms by something else that can bond to carbon, and that something else can be another substituent of some sort. And there is below that there is a structure in which we've done exactly that. Although you've got the central carbon now is attached to 3 other carbons. If you count up the hydrogen atoms, if you count up the carbon and hydrogen atoms, you'll notice it is still C4H10. So the molecular formula is the same, but you have a different carbon chain or different carbon skeleton. Now, there's a lot of ways when you get up to a butane. There's only 2 ways of writing a C4H10. But there's I think only 2 for C5 for pentane. But as you get higher up, you get very large numbers of possible structures of these things. So you can. I was looking at something on the internet, looking for some examples, and for C50, I think C50 or maybe C100. I'm pretty sure you have something like 10 to the 21st possible structures of these. So we need ways of naming these things, of describing them, because drawing out these structures can sometimes be tedious. And even if we're drawing the structures out, we're going to have to, and we're writing this up, we're going to have some way of writing the name of the compound. So that's the idea of what we're doing here, is to write the UPAC names, IUPAC names for alkanes with substituents, and draw their condensed structural or line angle formulas. All right. So what we're talking about here is structural isomers. Given a molecular formula, you may be able to, many times, in fact, I would say most of the time, because if you're using larger molecules than 3 carbons or 4 carbons, you're going to have a number of different possible structures. So what we call these different structures that have of identical molecular formulas, we call them structural isomers. So you see butane has 2 structural isomers, and I do have something in here. This is what I wanted to mention. Okay, let me see. I'm going to see if I can adjust this. Okay, notice here, I've got my notes here, and you notice that as you have 3 C5H, that should be C5H12. This is a typo here, so let me change that. That's a typo. But the numbers rapidly increase after C5. You got 24 compounds with C8H, 24 compounds with C8H18. That means there's 24 octanes. Now they're going to be named in different ways. They're not all going to be named octanes. In fact, most of them aren't. You have 136 with C10H22, 3,396,844 with C20H42, and you get up to H50, which is 2.5, which is a little 2.5 times. You see, you've got 10 to the 21st, and with C100, you've got 10 to the 40th. So you have a lot of 10 to the 40th is, I think, that's. We've got the number of moles of formulas for that. So you see, we need a way of writing the names. So that's how we're going to do this. Now, they say there's something they mentioned here. The butane, one of the C4H10 isomers, is a straight chain and another one is a branch chain. I don't really like the straight chain designation. I don't like the word straight chain I don't like the term straight chain in this context because, first of all, these things are not straight in 3 dimensions. And second of all, they're not straight. They're not straight lines. And you'll see what I'm talking about when we get into naming these things. I like continuous chain better, but it's whatever you prefer. So now we draw 3 possible structural isomers of pentane. Well, I just told you there's 3. But let's do these. Let's do the whiteboard. Let's clear this. We have C5H12. And pentane, C5H12, structural isomers of pentane. Okay, so draw the 3 of them. Well, C5H12, you can do this one. Okay, C3, H2, 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 CH2, CH3. Okay, they do say condensed structural formulas. Right? Draw 3 possible structural isomers. Okay, they don't really tell you explicitly which type of notation to use, so we'll stick with the condensed structural. Okay, well, you have this chain here of 4. So let's take. Now let's play. Well, you see what happens when you play around with these things. Okay, let's say we've got 1, 2, 3, 4, 5. Why don't we take this methyl group and move it? Well, where are we going to move it? Okay, let's say we have. I'm just going to write one of the. Now we've got that. Okay, so if you put it on one of these N carbons with the CH3s, you're just going to have a straight chain again. See, there I go, a continuous chain, but you're still going to just have pentane. So the only place you can put this thing is going to be on one of these 2 internal carbons. And you can really do either one. If I did it this way, I can do it like this. No, I don't want to write it that way. We're trying to do it like this. CH3 like that, and then CH2 and CH3. Now, if I put this thing, okay, I'll write this other one here. I could write it like that. That's the same compound, as you'll see when we talk about naming them. That is really the same thing. Okay, so we've got this one now. Let's work with this one. So we've got here's our number 1. Here's our first isomer, and here's our second isomer. They say 3. Okay, what else can we do? We can take another methyl group. Let's take this one, and where are we going to put it? Well, we have okay, you see this carbon atom is now going to be CH3. We already have CH3 here. And we got to put this methyl group somewhere. Okay, well, if we put the methyl group on any of the CH3s, we're going to be back to this structure again. So it's got to be down. It's got to be the central carbon here. Let me see if I can get that. And I'm just going to have to rewrite this. So there's going to be a carbon there and CH3. So there's going to be a third one. So you see, you can branch these things out quite a bit. And what they do is what they give you is there. So you see what I just did. It's there's the condensed structural formula and the line angle formula. So we can let's go back to the whiteboard and go ahead and this one's going to be 1, 2, 3, 4, 5. Okay, that's one of them. This one's going to be 1, 2, 3, and 4. Okay, 4 carbon. Now we've got to account for this one, so you'd write it like that. This one is going to be 1, 2, 3, and then there's 2 methyl groups on the central carbon. So that's the way you're going to write those, and that's the way they do it. Alkyl substituents, you've got to know some names of these things. Their substituents are atoms or groups of atoms attached to carbon chain and include alkyl and halo groups. Okay, so alkyl groups are groups of carbon atoms attached to carbon chains, and they have carbon with hydrogens on them. Alkyl groups are like CH3, and you'll see them shortly. They are really named in the IUPAC name system. They are named with an YL ending ill. So what you do with those is you take the parent hydrocarbon for that particular substituent. If it's methane, you remove a hydrogen that is now methyl, and you can use that. If we go back here, we've seen a lot of methyl groups here. You see the CH3s, those are methyl groups. And you're going to see how to name these things. Halo substituents are halogen atoms attached to the carbon chain. They form very strong bonds with carbon. And they are named by removing the INE of the halogen name, fluorine, chlorine, bromine, and iodine, and replaced with an O, so fluoro, chloro, bromo, or iodo. And here are some of these groups, some of these common groups, which the ones you need to know, and the ones you're going to be responsible for. And you see the 1 carbon alkyl group is methyl, 2 carbons is ethyl, 3 carbons is propyl, and there's another one. There's 2 possible 3 carbon structures here. You can have this alkyl group is going to be bonded to something else, okay, and then you have a propyl group is the straight chain, the continuous chain on one of the end carbons is where the substituent is attached to something else, and in the isopropyl group, it's the central carbon that's attached. So keep those in mind. Butyl, there is butyl, as you see, a 4 carbon chain with the attachment point at one of the end carbons. And there's an isobutyl group, which is now you have you have a branched chain there of 4 carbons. And we call that configuration isobutyl. All right. So this is let's say this is CH3, CH2. This is a condensed structural formula that's even a little more condensed. Butyl, straight chain. Now you have this one CH3. Let's do the regular. Do it the way they do it in the book. And that's isobutyl. If you play around with these things, you'll find there's actually a couple more. There's actually a couple more of these, and I'm not sure they talk about these in your text, so we're not going to go to them. But you can look at. I'll draw. I'm going to draw them for you. Okay. There's just so you can see this. You can also you can have this one. And we call this secondary butyl. I'm just doing this for completion. They're not going to really, I don't, like I said, I don't believe these show up new text. I don't recall. But this one is called, this is tertiary butyl. So you see, when you start adjusting the chain, when you start writing all the isomers and all the possibilities, you see, you start seeing, you get a lot of possible combinations of these things. So, but those are the propyls, propyl and isopropyl, butyl and isobutyl, you need to know, and fluorochlorobromo and iodo. So, unfortunately, they didn't really give any slides here to explain the procedure. So we're just going to go through. We're just going to go through these slides. This is the names are in it is. They explain it. There's a sample problem 11.4. They do it by sample problems here, so we'll go ahead and do it the same way they do. But let's just do this one. This you have, look at what you have here. You have a 5-carbon chain with a chloro substituent on one carbon and a methyl substituent on another carbon. Now here's where well, let's go to the next slide. We'll talk about how we do this. Analyzing the problem here. This is the, okay, you write, when you do this, first thing you do is you find the alkane name. Now this is not an alkane because it has a chloro substituent, but it's going to be named as an alkane. And you want to find the longest continuous chain of carbon atoms. Now notice, you can count your carbon atoms in a lot of different ways. You could start from here, this carbon 1, 2, 3, 4, 5, or from the other side 1, 2, 3, 4, 5. What about this? 1, 2, 3, 4. 1, 2, 3, 4. Well, no, okay, so this methyl group is not going to be part of that. And you got a 5-carbon chain, so it's going to be a pentane. That's the first thing you do. First thing you have is a pentane. So first thing, longest chain of carbon atoms. Now, you have to number, you simply put numbers, you number the carbon atoms, and you put, you give the substituent, well, you put a number by the substituent, then you write the substituent, and then you go on. So in this, and you use the lowest possible numbers. Okay, so the way this is done, you see that the chlorine, the chloro substituent, is on the 2-carbon, and the methyl is on the 3-carbon. The way you write this, though, is you give the location and name for each substituent in alphabetical order. And the alphabetical order does not include, dimethyl, trimethyl, stuff like that. It's just methyl. So 2-chloro, 3-methyl pentane. Let's see what else they want to do here. Cycloalkanes with substituents. It's pretty much, it's the same type of thing, although with a cycloalkane, if you have one substituent, that's automatically the one position. Since all the positions on cyclohexane here are identical, wherever you put an ethyl group is going to be the same. And there, you don't need, with one substituent, you don't really need to put a number on it. So it's ethyl cyclohexane there, or it could be propyl cyclohexane, or chlorocyclohexane, or something like that. Now, you can get more than one of a given substituent on one of these things. And so you're going to need prefixes for those, di, tri, tri, tetra, penta, stuff like that. You can get these long, you can get a lot of these different things. And they're asking you to draw the structure here for 1-chloro-1,2-dimethylheptane. Okay. Now notice the way it's written. Okay. Well, in this case, it's chloro and methyl. The alphabetical order is chloro and methyl. That di does not work into the order of these things. So, well, let's write this thing out. Okay, 1-chloro-1,2-dimethylheptane. Okay. Now we know it's a heptane, so it's going to be 7 carbons. Let's try this again. 1-chloro-1,2-dimethylheptane. Wrong. I just showed you how this is done. 1-chloro, 1,2-dimethylheptane. Now notice the way this is written. A number, a dash, and then the substituent, and then another dash to separate from the next. Let's see, right. Okay, 1-chloro is the first substituent. There's a dash. 1,2-dimethyl is the next substituent, and then heptane. Okay, there's no dash between the last substituent and the heptane. All right. The way we're going to write this out, the way we do this is, it's a heptane, so your longest continuous chain is going to be 7 carbons. So let's put together a carbon. See, 1, 2, 3, 4, 5, 6, 7. Okay, there's our 7 carbons. So we got the heptane done. And we know this is going to be saturated. We know there's going to be all single bonds because of the ane, AN. Okay, 1,2-dimethyl. We can, wait, is that right? 1-chloro, 1,2-dimethyl, yeah. All right. In principle, we can go from either side. I'm not really sure if I've really seen a trend either way, but we'll start at this end. Okay, 1-chloro, 1,2-dimethylheptane. All right, so there's a 1-chloro. So we're going to just call this the 1 carbon. 2, 3, 4, 5, 6, 7. Let's write this out. Okay, we put a chloro here. And then 1,2-dimethylheptane. Something's wrong with that. Because you put this here. 1, 2. Geez, I missed one. This is an impossible structure. All right, so I'm guessing that they meant 2,2-dimethylheptane. So let's write 2,2-dimethylheptane. And there, when we do that, we're going to have and this is what we're going to this is going to be our structural formula. When you start putting the substituents on, you end up with ways of putting this. This is going to be probably write something like this: CHCl, CH2, C, CH3, 2, CH2, 2, 3, 4, 5, 6, 7. That looks right. And if you want that's a condensed structural formula. And if you want the line angle formula, let's say we go, 7, 2, 3, 4, 5, 6, 7. And there's 2 there and a chlorine here. And that's what I'm guessing that is. Let's see if I'm right about that. Okay, they don't even do this one. But that is, okay, this compound is, you know what I'm going to do? I'm going to change this right here. I can't change. I'm going to have to go in and change that elsewhere. That is definitely wrong. But let's do 3-bromo, 1-chlorobutane. Now that is a possible compound. But you have this one for if you want, 1-chloro-2,2-dimethylheptane. That is going to be a real compound. So draw the condensed structural line formula for 3-bromo, 1-chlorobutane. Okay, 3-bromo, 1-chlorobutane. We'll do that. Okay, 3-bromo, 1-chlorobutane. Okay, you've got a butane, so you've got C4. And condensed structural formula is what they want. So, but let's put this stuff in here. One chlorobutane. Okay, 1-chloro. You notice 3-bromo B C. Okay, so you've got there's that alphabetical order there. Well, 1-chlorobutane. Well, it's got to be an N carbon. So let's pick this one. So we'll have chlorine there, and 3-bromo. That's 1. This is the 1 carbon. Then we go 1, 2, and 3. So there's a bromine there. Now we fill in the rest of the bonds, and that is our condensed structural formula. Let's see how they write this thing. Well, we saw the four bonds. We did that. That was the first thing we did, and you fill these things in like this. Okay, this is exactly the same way we did it. And then you fill in these. You fill in the hydrogen atoms. Now, okay, they wrote it a little bit differently than I did. Okay, no, they wrote it. Let's say CH2, CH2, CH, CH3. Notice I put the chlorine. I stuck it out from this end. That's a perfectly legitimate formula, and so is this a perfectly legitimate formula. You can angle these things any way you want. Sometimes you might have a reason to write it one way or another. But yeah, there's your I have a note here to myself. The carbon atom is stable organic. Okay, any carbon atom in a stable molecule is going to have 4 bonds to it. All right, so again, with the line angle formula, anything here. Let's okay, right here. Well, I'll draw this here, this line angle formula here. This site here, that's a carbon atom. This is a carbon atom. This is a carbon atom. This is a carbon atom. We're in these line angle formulas where no substituents are indicated or are written. You assume that whatever bonds are left over are to hydrogen. Okay, so this is a carbon atom with a chlorine attached to it, and this carbon attached to it. So there's going to be 2 H's assumed. Same thing here is going to be 2 hydrogens assumed, only 1 here, if you think about it. And then 3 here. So that's what these things mean. So let's name these following alkanes. Well, let's just do this. Let's try to do this verbally. What's the longest chain in A? Well, there's only one chain. It looks like 2, 4, 5. It looks like there's 5 carbon atoms in a chain. No, it's there's the ends. There's 2 carbons there, and then you've got the 3 angles there. So there's 5 carbons, and there's a chlorine on this on 1 carbon. Well, it looks like if we started. Well, I'm going to do this, so I'll show you how we do this. All right, it's a 5 carbon chain. We saw that. 1, 4. Now here's what you don't want to get into. Remember, I was numbering from left to right. Well, a lot of times numbering from right to left is very common. So you might look at this and say, well, 1, 2, 3, 4. That's wrong, because you need the lowest possible number. With a 5 carbon chain, something on 1 carbon from one, this thing's attached 1 carbon from one end. So this 1, 2, 3, 4, 5. Okay, so you can have, it could be 2 chloro or 4 chloro. 4 chloro is wrong, because 2 chloro is the lowest number. So this is going to be 2 chloropentane. And we'll go to this other one here, which was this one. Now what do we have? Because we got to be careful about this. A lot of different ways we could pick chains here. We start here. These are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. Okay, so this is going to be a 5 carbon chain. All right, so 1, 2, 3, 4, 5. 5 carbon chain is going to be pentane. Now we have to number that somehow. We need the lowest numbers. All right, so if this is a carbon. This is a carbon. I'll tell you what. Let's. Here is our parent chain. And now what do we have on it? We've got a methyl group here. Okay, remember this is a methyl group. This is a methyl group. That's the line angle situation. All right, so we're going to have to number that somehow. Well, this one is on the 2nd carbon from this end, and this one's on the 3rd carbon. If we number from here, we're going to have 2, 3. You're going to have 3 and 4, and number it from here. It's 2 and 3. You want the lower numbers. Okay, so this is going to be 2, 3. Okay, there's 2 methyl groups here, so that's di. So it's 2, 3 dimethyl pentane. All right. Okay, longest chain, pentane, 5 carbons, and 2,3 dimethylpentane. There you go. And so you're done. So these are the ways that this is how you name these things. And there's that's the end of, well, that's going to be 11.3 now, and we're going to be moving on to properties of alkanes, which is fairly short. I'm going to do that one, and then I'm going to take a break I'm going to take a break and get this thing loaded. So let's do section 11.4, which should take care of, which is going to take care of alkanes, and then we're going to get into some other hydrocarbons. So we're going to move over to 11. Properties of alkanes. These are, alkanes are, they show up here and there. in like plants, like in waxy coatings on fruits and vegetables. They're actually secreted by the plant or by the fruit, and they help to protect it from the elements to some extent. And they protect they protect the fruit from the elements simply from by virtue of the fact that they are nonpolar and they don't dissolve in water. They are very and higher molecular weights. They will burn, but they're actually pretty stable unless a source of ignition is there. So aside from that, we go on to just the small ones on up to the large ones. You have methane, ethane, propane, and butane. These are gases at room temperature. Remember, these are nonpolar molecules. They don't have very strong intermolecular attractions. There is such a thing as a hydrophobic interaction or nonpolar interaction, something like that, but they're not very strong. So the lower molecular weights, those four tend to be gases. You will have butane. Well, cigarette lighters, you get butane lighters. There's a liquid in there that is butane. That is a butane, but it's under pressure. You can liquefy gases under pressure, and you may know that. 5 to 8 carbons are highly volatile liquids at room temperature, which makes them useful as fuels. So you have 5 to 8 carbons, but then you have 9 to 17 carbons are higher boiling, and you can find these in motor oils, mineral oil, kerosene, diesel, and jet fuels. You can get these things to burn. You pretty much have to get it into the gas phase to make it burn, and it's harder to do that, but it can be done. And then when you get 18 or more carbons, you're going to get paraffins. Paraffin comes from Latin meaning low affinity or little affinity, which means that they don't have, they really don't react a lot. They don't interact with things. They don't dissolve in water. They don't do much. So then you get higher molecular weights. You have petroleum jelly or Vaseline. It's a semi-solid mixture of hydrocarbons with more than 25 carbon atoms. So you can get, you go chains of, polyethylene is really, really, really long chain alkanes is what it is. So those are the basics of the physical states of these things. They're nonpolar, so they don't dissolve in water. They're less dense than water. They'll float on water. Some of the polymers are denser than water, but the basic alkanes that you're going to be interested in, that you're worried about, are going to be much less dense, quite a bit less dense than water. They're flammable in air, and that's what's found in crude oil, are alkanes. Mostly, there's a lot of alkanes in there. You can get alkanes out of crude oil. The oil spill in the ocean, you see the oil is going to float and cause a lot of problems. There's going to be some denser materials on the going to be on the floor, but those mostly aren't alkanes. They're other compounds, and we'll see those types of compounds. We're not necessarily going to talk about them though that much. So that. Again, combustion is one of the key properties of these things. They will burn, and actually, combustion there's a couple of other reactions that alkanes will undergo, but other than combustion, for the most part, alkanes really don't do a whole lot. They don't really do much chemistry. And what happens is when we get further on and later on in this lecture or in these videos in this module, you're going to start seeing alcohols. You're going to see aldehydes and ketones, and you're going to start putting other more polar groups on it. And when you get these, then that molecule is going to start doing some serious chemistry other than simply burning. So you already have seen this reaction, this type of reaction, combustion reactions. You've seen that before. So you should understand that pretty well. Here's combustion of butane. There's the reaction of butane with oxygen to get carbon dioxide and water and energy. And there's this learning check. So they want you to write a balanced equation for propane combustion. To write a balanced equation for the complete combustion of propane. Okay, so well, let's do that. Let's do it. Let's clear this. One combustion of propane. I'm going to go back here. I want to take a look at how they write these because I'm curious about the water. Okay, the water, they put the water as a gas, which is okay. Okay, we're going to do it the same way they do. We have C3H8 plus O2 is going to give you carbon dioxide and water, H2O. Okay, carbon dioxide. So let's say this is going to be a gas. 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 And energy. Okay, so we have C3H8 burning in oxygen. Now we have to, well, let's start changing coefficients on these things. Let's take a look at what we have. We've got 3 carbon atoms. And the only place carbon goes is to carbon dioxide. Okay, so whatever, now here's something to keep in mind. Anytime you have these relationships, when you're always going to have 3 times as many CO2 molecules as you have propane molecules because there's 3 carbons on a propane and only 1 on CO2. Okay, so let's change this to 3. And, well, water, you only have water, you have hydrogen in one compound here and one compound here. So, well, okay, there's 4, what we have here, there's 4, 8 hydrogen atoms. So that's going to give you 4 water molecules. So there's that. And it looks like we're in pretty good shape now. Remember, we saved the elements till last. And we have to balance oxygen. So carbon's balanced, hydrogen's balanced. Now oxygen, we've got 3 times 2 for carbon dioxide, it's 6, and then another 4, that's 10 oxygens. Well, 10 oxygens is going to require 5 oxygen molecules. So now you got 10. So that should be the balanced equation. And it looks like that's what they have. It's pretty much the same order we did. Sometimes you might do this in a different order, but it's I put in something here. The notes that I wrote to myself here. As you go through this chapter, you might want to try writing some balanced equations for some other combustion reactions, but our metabolism is largely based on the combustion of glucose, C6H12O6, and fats. You might look ahead and work out a balanced reaction for combustion of glucose and let's say tristerin, which is it's a fat. It's a triglyceride that's going to be found in animal fats. And you see those are pretty monstrous looking things. You don't have to do it, but I put those in and you can try playing around with those. Okay, that's alkanes. We're going to move over into we're going to the next section is going to be alkenes and alkynes, and that's going to be a separate video from this one. So we will see you later.